And with that, I'm going to welcome Jim. The floor is yours. Thank you very much, Jim. Looking forward to your talk.
Thank you, Michael. Why don't we go ahead to the next? As we're getting started here, I will just let everybody know that what I'm going to talk about is mostly not my work. I managed the study, but all of the real work here was done by Fazil Sadiq, who's here to help answer some questions, and also Wayne Schley early on in the study, and Amanda Hapalachak, who I think is not going to be able to be with us today because she has a sick child. At any rate, I'll give you a summary of what we did for the trajectory analysis for the mission design. I would encourage you to look at the concept study report when it comes out, because there's a whole lot more detail there. Having said that, let's talk a little bit about nomenclature. We did have a big study to do. There were 3 different opportunities for trajectories, 3 different trajectory classes, if you will, that allowed us to escape with high velocity. I list the 3 options here. So one is a ballistic Jupiter gravity assist, which is essentially just a launch to Jupiter and doing a gravity assist there. It's a 4-stage launch vehicle. And I think we've talked a little bit about that before. There are 2 different variants of that. So we have an option 1A and an option 1B. Option 1A is the heliophysics focus with the baseline example payload. That one is our baseline mission concept. And then the variant B then adds changes out the payload to be the augmented payload, which you heard about yesterday. Option 2 is a powered Jupiter gravity assist, and it's a very similar mission to the ballistic Jupiter gravity assist, except for here, that 4th stage on the launch vehicle, the solid rocket motor, is going to get carried with us to Jupiter. And then at perigeo, we would fire that motor to give us even more speed from the gravity assist. And then the 3rd option is what's called a solar over-Earth maneuver. This is a much different one, and I'm going to hold off a little bit on talking about that one until we get to the end, because it actually is it's very different from the other 2 and really kind of deserves its own mission design and flight system design and so forth. So with that, let's go to the next one. Great. So here's our process. The first thing that we want to consider is what is achievable for these options, right? So if we're looking at the sky, which directions can we go in the sky and what years can we go? And what are the speeds that we can achieve whenever we get there? So the process we went through looks something like this. We know that there's a Jovian cycle here. We were looking at the 2030 to 2042 launch years. That's kind of a full cycle, if you will. And for each of those launch years, basically we're generating a sky map. And that sky map is just a map of latitude and longitude in the sky, where we color code it by the speed that can be achieved for a particular direction. This is dependent on launch mass in the launch vehicle. So we had to kind of nail those things down at first, and I'll show you our assumptions here in a minute. Basically, each latitude and longitude point is a direction that could be targeted. Right. And just for practical purposes here, whenever we talk about speed or escape speed, we're really talking about the speed at 100 AU for almost all of the cases that we're looking at here. And that's following a Jupiter gravity assist that targets that particular direction in the sky, right? If you look at these sky maps, what you see is every year has a hot zone, and that hot zone kind of moves around in the sky depending on the launch year. And then what we want to do then is take a look at the aggregate case, the aggregate sky map. And so you've probably seen, or some of you may have seen some of the sky maps that we presented in the past. That's essentially what we're looking at, is that aggregate map over the years that we're considering here. We can also put other features on that map, like planetary bodies, the IBEX ribbon, all of those kinds of things. And what that does then is allows us to present to the science team the set of options that they can consider for where they want to go in the sky, how they want to do the science of the mission. And then they take that, and they've used some goals to try to pick out those areas of the sky that are of most interest. One of those goals was to reach the heliopause and interstellar medium quickly. So we're going to be looking at the hot zones. We want to capture a side view of the heliosphere. And so if we know where the nose of the heliosphere is, then we're looking at angles up to about 45 degrees off of that, I think is the primary consideration. And then there's a great desire to intersect the IBEX ribbon if possible. And so that was also part of the consideration for picking a particular target point for a particular launch year. So why don't we go to the next one? So this is the sky map for the baseline trajectory. This is, again, the 4-stage launch vehicle using SLS Block 2. the Centaur and the Star 48 solid rocket motor as a fourth stage. This is the passive Jupiter gravity assist case. And let's see, I think the other thing I wanted to say about this is, well, I had the thought, now I've lost it. Oh, the spacecraft mass here. This is for a spacecraft mass of 860 kilograms, which is that baseline flight system configuration that I presented on Monday, I think it was. So if you look at this, the nose here is, I wish I had the mouse, but the nose here is at about 250 degrees, 55 degrees or so. Yes, there it is right there. Thank you very much for showing that. The purple sort of what should be a circle, but really is kind of distorted because of the way we're plotting this, is the 45-degree cone plus or minus, I think, 5 degrees on either side of the 45-degree cone. And that is showing sort of the range of places where we'd like to look at the heliosphere from the side. And if you do that, then you can see, and I don't think that they're presented very well on this plot, but in the when you look at the plot that's in the concept study report, you'll see that there are launch years also labeled for each of these. And then, so if we look at our target, which is about 180 degrees east and about 22 south, that is for the launch year 2036. The one next to it to the right is 2037, and then 2038, all the way over to the end of the other side of that purple band, if you will. That corresponds to late 2040, early 2041. All right, so these are the targets that we considered, and whenever you read the concept study report, you'll see that there are launch targets available for each one of those years. We'll talk about, I have a slide here where we'll talk about those, I think, next. Yep, there we go. Well, this is the baseline trajectory, so that's good for now. We've picked the 2036 case because that's sort of the earliest of those really favorable science trajectories that we wanted to look at. Honestly, we could pick any launch year from 2030 all the way to 2042, and there's a science case to be made for any of those. Some of them are more favorable than others. When you look at sort of from the solar system from the top, this is what the trajectory looks like. It's simply a flight out to Jupiter and then a change of direction to Jupiter to send you out on the course that you want to go. For 2036, this is a launch between the 28th of August and 18th of September. So we have a nice, the usual 21-day launch period. Across that launch period, we can get 6.8 to about almost 7 AU per year. One of the reasons why that speed is a little bit lower is because we've intentionally picked a target point that's off the ecliptic, so we could intersect the ibex ribbon. A trade could be made as to whether that's something that we would want to pick if we were looking at it at the real mission. If we were to move more towards the ecliptic, then that speed gets up to more in the 7 to 7.3 or so AU per year. And this gives us less than 15-year flight time to 100 AU. I also show a table here that gives you kind of the breakdown of what the mission would look like in a global sense if we were to choose this mission. Launch and checkout is something like 2 months. The total cruise to Jupiter then is another 7 months for a total of 9 months, I guess, to Jupiter. We spend a little bit of time at Jupiter. There's a few weeks before when we're prepping. There's a few weeks after when we're cleaning up. So we think of a JGA phase, if you will, as being that sort of couple months period or 8 weeks period, looks like. Then after that, in this case, we would show a wire antenna deployment. It takes about a month to do that. Could be done before Jupiter if we chose to do it that way, and likely would if we were to choose this particular mission. And we talked a little bit about what that means in terms of spinning up the spacecraft and slowly releasing these wire antennas out. Then that's followed by the primary science mission, which is an interheliosphere phase for about almost 12 years, then the heliosheath, which is about a 4-year crossing, and then the interstellar phase, which is another 33 years, right, for a total, for the total of 50 years. And then after that, there's an extended mission. So this is the kind of mission that we would look at with the passive Jupiter gravity assist. So why don't we go to the next slide? I just threw this in real quickly because the launch period, as I said, we've got a 21-day launch period that that is better than 6.8 AU per year for that whole launch period. That's pretty typical for NASA missions. What that means is this is a relatively low risk launch period. It's not like we have just a few days and we have to make those few days. Here we've got some time, typical for things like New Horizons or Parker Solar Probe or other big missions. spacecraft mass. So we did look at how the flyaway speed, the escape speed, depends on the mass of the spacecraft. So within the ranges that we're talking about here, we do see a linear relationship between mass and speed, and you get about a 0.17 AU per year change for about a 50 kilogram change in mass. And that's really nice, because what that means is we have the flexibility to make some trades with payload, to have some margin in the spacecraft. And so there's a nice box here that we can live in that allows us to make those optimizations. And it's also risk reduction, because if late in the game we find out that we need a little bit more mass, okay, we can do that. We're not falling off a cliff. Maybe we go a little bit slower, but at least we got a mission, right? So there is some risk reduction there. For launch year, as I said before, we do have launch years that meet the selection criteria that exist from 2036 to 41. Why don't we go to the next slide, and I think we'll show that a little better. Yep, here we go. So slightly different map. It's the same map, just plotted on a different projection, but it's just to kind of emphasize things here in the middle. But in the table that you see here, you see the launch year 2036 and 2040. You see some possible targets, and you can see the escape speeds there given those targets. Again, the 2036 and 2037 are a little bit lower because of the wanting to go off the ecliptic to intersect the IBEX ribbon. If you didn't want to do that, you wouldn't necessarily pay that speed penalty. As you get further out, though, you're more in the ecliptic and you're able to see the IBEX ribbon. So let's go to the next one. This is the Skymap for the powered JGA. The mass of the spacecraft is a little bit bigger, but they look very, very similar. And the speeds are a little bit higher, so up to about 0.5 AU per year, greater than for option 1. This mission is going to be a lot more complex, though, in the sense that you're taking the solid rocket motor along with you and firing it at Jupiter, where there's lots of radiation, and we've got to keep it, at the right temperature for all those months out to Jupiter and so forth. So while you do get a bit of a speed boost here, it is not that much of a speed boost when you compare it to the risk that you incur. Let's go to the next one. All right, so let's talk about the solar orbit maneuver for a minute. First of all, let me just tell you what that is. So first of all, you're going to launch the flight system. You're going to cruise to Jupiter and do a passive Jupiter gravity assist there. That gravity assist is going to target a perihelion around the sun. For the purposes of our mission here, we're looking at things between 2 and 5 solar radii, which is something like a factor of 2 to 4 deeper in the corona than Parker Solar Probe was achieved, right? And so the temperatures are much higher. You would then execute that Oberth maneuver at whatever perihelion you chose, and then would cruise out away from the sun for probably until about 0.75 AU, maybe 1 AU. Then you would separate the observatory, and then that would then begin the primary science mission, right? I list over here on the side some issues and concerns with that. There are lots of them. The main ones are things like asymmetries in the heat shield that are going to cause very large torques from solar pressure. Any imbalances in the system here are going to be greatly affected by the fact that you've got this light hitting the heat shield and causing torques. We're worried about the center of mass that shifts during the solid rocket motor. There's 6,000 pounds of propellant in the solid rocket motor, and you're burning most of it away. And so as you do that, the center of mass shifts, and what that does is it causes these large, essentially uncontrollable torques on the system, unless you have some sort of secondary propulsion system that's gonna keep the system control, right? I talked about the temperature a little bit. We have included in this flight system a balance mast, so basically ballast for the spacecraft, to keep that center of mass of the flight system along the thrust axis of the solid rocket motor. It's dead weight. Even if you put instruments there, it's not clear you could do a whole lot with them, given the environment that we're in, and frankly, you need a lot of it. So it means that we're paying a penalty here for doing this that is going to wind up decreasing the speed that you could get out of one of these sorts of systems, right? And then we have other issues like how you place GNC sensors and so forth that make control pretty problematic. So let's go to the next one. I just want to show you what the flight system might look like. This is the kind of thing that we would fly if we were to do the solar orbit case, where you can see the solid rocket motor over on the left-hand side. There's this interstage section which connects everything together, and then the observatory or the spacecraft over on the left-hand side, or right-hand side rather. And then you can see the big heat shield that would be pointed towards the sun all the time, and the ballast. And you can see how tight it is to fit something like this in. and understanding that the bigger we make the spacecraft, for instance, the bigger the heat shield has to be, right? Or if we have RTGs that stick out, from the spacecraft, then they've got to be covered by a bigger heat shield. So there's some real trades and compromises you have to make here to make this system work. On top of the fact that we're not even sure we could build this heat shield. So let's go to the next one. This is what that mission design looks like. So you see the launch out to Jupiter, back to the sun, then out of the solar system, and you can see there's 850 days or so worth of trip before you even get to Jupiter the second time. That would parallel the option 1 mission, the baseline mission that we're talking about, right? So again, understanding that we could theoretically achieve higher speeds here. However, you're paying a penalty because it's going to take you several years even just to get to where a primary mission would be almost immediately within 9 months or so of launch. So let's go to the next one. So we did do some design trades on this. I'm not going to go into this slide too much other than just simply to say there was a big grid search that went on to try to find those trajectories for the solar orbit maneuver case that would work. We did find some of those. This is a point design, so it depends on the mass of the flight system and all that. We've assumed a 7,000 kilograms, a 7 metric ton mass for an observatory mass of about 900 kilograms. And you can see the other parameters that were fed into this calculation. And essentially what we find out is if you look at the speed at 100 AU, the maximum speed for this kind of configuration is only about 4.5 to not even 5 AU per year. And this is because we're really burdening the system with all this extra mass that we got to carry along, right? Just to survive the environment. And so this, combined with some other analyses that you can see in the concept study report, really leads us to believe that even if you could build a solar orbit case that would work, you would not achieve 100 AU or further distances faster than you would with option 1 or option 2. Right, so let's keep that in mind. Let's go to the next one. This is what the Skymap would look like. So what we've done is we've taken the option 1 Skymap and we've superimposed on that now the Skymaps for the solar orbit case. And you can see pretty quickly that what you get is a bunch of little blue dots, which are much lower speed, about a factor of 2 less than the speeds that you could get with option 1. So let's go to the next one. This is what it would take to actually break even. So suppose we wanted to build something that was equivalent to the option 1 or option 2 cases. The only way to do that is to reduce mass. We're certainly not going to make a bigger launch vehicle than the SLS. To do that, we've got to go from 7 metric tons down to about 4.1 metric tons to be able to equal the ballistic gravity assist, the option 1 case, or 3.7 metric tons to be equal to the option 2 case. And realistically, you're not going to decrease the mass of the spacecraft, the flight system, by a factor of 2. Okay. All right, let's go to the next one. All right, quickly some conclusions. First of all, we've done what we said we were going to do. We studied all these trajectories. I think, have laid out a pretty good case that the passive gravity assist option 1 accomplishes the science objectives with minimum risk. Option 2 can get you a little better speed, but it winds up adding complication and risk. And then option 3, the solar orbit maneuver, does not beat either option 1 or option 2, adds significant cost, complication, and risk to the mission, which is why we've chosen the mission we have for the baseline. It offers flexibility and risk reduction because of things like that linear relationship between mass and speed. We've got a good launch period that we can use that again is a risk reduction. And then we also have viable missions for a range of launch years. So suppose we wound up having to delay a launch a year, we could still do that and we would still have a very good science mission. And it also allows flexibility to allow the science augmentations simply with a change in target direction if that's what the community decided to do. And with that, I think that's my last slide. So Michael, do we have time for questions or did I use up all the time?
Thank you, Jim. We do have 3 minutes for questions. If there's any floating out there. You go through them so quickly and efficiently, Jim.
It's a lot of material to look at, and I will say
it really is.
There is a great deal more information in the, especially in the details of how the calculations were done in the concept study report. I would definitely suggest you take a look at that whenever it's available and dig into some of this.
We have one question from Rob Stoke, who I think is on our panelist side and maybe can't access the Q&A tool, but he asks, what is the peak launch declination for these years?
And Fazil, do you have that information handy? I certainly don't.
I don't have that information handy, but I think because we're living near the ecliptic, I don't expect it to be terribly high. So we would still probably be, compatible with launching out of the Cape, for instance, because the declinations would be within that 28-degree span that you need to be for the Cape.
Kirby asks, how fast is the spacecraft going prior to Jupiter gravity assist? In other words, how much speed do we get from Jupiter?
So I don't have that quantified, but I could always follow up with Kirby offline. But I mean, yeah, when we're leaving Earth with, the C3 of 300, so square root of that would be the relative velocity with respect to Earth. So I'm not going to try to do math on the fly during the webinar, about 15-ish kilometers per second, maybe.
I think some of the numbers we've looked at, though, basically point towards Jupiter doubling our hyperbolic asymptotic escape speed, right?
Yeah, I mean, and you can even tell by the plot that Jim had showed. There's a lot of bending that's going on in that plot. Jupiter is a massive nonlinear lever arm that we're leveraging to get that speed increase.
Very good, very good.
Absolutely.
Very good. And we do have one question in the Q&A. It says, will it be possible for students to access the study report? And the answer is absolutely. The report is still going through the editorial process. We do expect to be publishing it publicly by the end of November, before the end of November. And if you're signed up on our mailing list, you'll definitely get a notice that has occurred, which I guess is a good opportunity for me to play Pontus's role here and plug. Please sign up for the mailing list if you haven't already done so. So very good. So with that, we are at 10:30. Thank you very much, Jim. And thank you, Fazil, for helping out with some of the answers here.